All right. Now let's shift our attention then to addition to carbon-carbon pi bonds. And we've been talking about reactions with electrophiles. The last time we talked about the reaction of isobutylene with HBr. The HBr we can identify as an electrophile because the hydrogen-bromine bond is polarized in a way that puts a delta plus on the hydrogen, because hydrogen is less electronegative than bromine. We have the nucleophile on the pi bond, so there is our first step, which can make one of two carbocations. If we put the hydrogen on the end, we make a tertiary carbocation, or if we put the hydrogen on the carbon of the alkene that has the methyl groups, we end up with a primary carbocation. Two pathways to choose using our standard idea of more stable, in this case intermediate. The carbocation is the major pathway. So the more stable tertiary carbocation, that's going to be our major pathway. It doesn't mean that none of the primary carbocation is formed. It simply means that there's more of the tertiary. Now we're not done with this because carbocations, for the most part, are not the kinds of things we can put in a bottle. They're pretty reactive intermediates, so they're usually not reaction products, and we need to continue on. And when we see a carbocation in a reaction mechanism, regardless of where it comes from, in this particular case from protonation of a pi bond, what do we think about? Resonance, which is not an issue here. And some people have asked, by the way, on the discussion board why we think about resonance, so let me address that. A couple of reasons. Number one, resonance gives us an idea of how stable the carbocation is and how easy it is to make. Number two, resonance contributors can lead to sometimes different products. If the positive charge is on different carbons, they may lead to different products, so it's something else to think about. No resonance here, so it's not an issue. After we thought about resonance, we then think about three fates of a carbocation. Now, there's no particular order to think about them in generally, unless you absolutely positively have to. In this case, we don't, but we also know what we're trying to do, and that's addition. So often capture a nucleophile. We'll finish the addition. What nucleophile should I capture? Br minus is my nucleophile. Somebody said water. No water present. Can't use that. Can only use what's present. We made the Br minus in this step. If you tend to forget that it's present, feel free to write it. We often don't write leaving groups or conjugate bases after they have left, but feel free to include them if you tend to forget that they're there. All right, nucleophile is captured by carbocation there and there. And we end up with, oops, bromine on the wrong carbon. The tertiary bromide from the tertiary carbocation and the primary bromide from the primary carbocation. The more substituted, the tertiary bromide is the major one because that was the major it was produced from the major carbocation it was produced. And you'll notice that this case we've added the HBr. I'm not implying anything about the geometry of the addition. I'm simply saying where the hydrogen and the bromine become attached. It was noticed a long time ago in 1870 by a Russian named Markovnikov that when molecules containing hydrogen on one end and something else add to alkenes, they tend to add in a way that the hydrogen becomes attached to the end of the alkene that has the most hydrogens to begin with. An empirical observation that became known as Markovnikov's rule. If you want to remember it, you can write it out in a long statement or remember simply them that has gets. The end of the alkene that has the most hydrogens gets more hydrogens. The rich get richer. So this is our major product. Now, when Markovnikov stated it was an empirical observation and no explanation really was offered, nowadays we know, at least in the case of HBr and HCl and things of that nature, that it's based on carbocation stability, but Markovnikov didn't know about carbocations. Heck, the electron was still 28 years down the road, 1898, from Markovnikov's PhD thesis. So the idea of carbocations way in the future. Now, I'm going to talk today about, first we're going to talk about addition to an alkyne. We'll do HBr to an alkyne. And last time we said we expect similarities in the reactions between alkenes and alkynes because they both contain carbon-carbon pi bonds. So let's see if that's true by working out the mechanism for addition to an alkyne. So the case I'm going to do here is, let's take phenylacetylene is a good choice. And remember, pH is benzene ring, and I'll react it. I think we'll use HCl this time instead of HBr, but it'll be the same idea. So we have a carbon-carbon pi bond. We have an electrophile, delta plus on the hydrogen, delta minus on the chlorine. You might also think of it as an acid, which sure enough, that's what it's going to do. It's going to protonate the pi bond. Pi bond being protonated. Now, because this is an unsymmetrical pi bond, it's not the same on the two ends. We have two carbocations to decide between. And my possibilities for that are this guy, where I've put the proton on the end, or this guy, where I've put the proton next to the benzene ring. Between these two pathways, the major one will be the carbocation, which is more substituted. More stable is the better word. Often more substituted is more stable, but remember, less substituted can be stable if resonance is involved. So let's see what my choices are. This carbocation, is this one methyl primary, secondary, or tertiary? Secondary. Remember, benzene ring, there's a carbon here. So this guy is secondary. And this carbocation is methyl primary, secondary, tertiary. One carbon directly attached, primary. Does the top carbocation have resonance? Yes, because it's the positive charges on the carbon next door to the benzene ring. If you don't see that, draw out the resonance contributors, so secondary with resonance. Tell me about that bottom carbocation. Does it have resonance, importantly, since we're talking about carbocation stability, does it have resonance which stabilizes the carbocation? It has resonance within the benzene ring. Every molecule that has a benzene ring has resonance. But the question is, does that resonance enhance the stability of the carbocation? No, it's too far away, so that's just primary. So clearly secondary with resonance is the one we're going to pick. Now at this point, some people say, but wait a minute, there's a double bond here. Shouldn't we have resonance with the positive charge? No, remember, to do that resonance, the carbon with the positive charge has to be next door to where the pi bond is. If this positive charge is on that carbon, as it turns out, the orbitals are perpendicular to each other. They don't line up, so they can't do resonance. You've got to be next door to have resonance. All right, so let's continue our mechanism. If that's the carbocation we're going to use, every time, you can say it with me. We're going to hear it a lot in this course. Every time you see a come on, say it with me. Every time you see a carbocation in a reaction mechanism, regardless of where it comes from, resonance, you've just done, and then three fates. You should get to the point where every time you see a carbocation in a reaction mechanism, regardless of where you are. So if you're driving down the 405 freeway and there's a billboard that says, have you studied Chem 14D today? And there's a carbocation right through your mind without any thought should go resonance, right? And three fates. So three fates. Which fate should we use? Now, again, rearrangement, lose a proton, capture a nucleophile are all possibilities. We're trying to get to an addition product, which probably means capture a nucleophile. But let's talk about the other things while we're at it. How about lose a proton? Could that happen here? Be deprotonated, form a pi bond. Yeah, actually it would just go right back where it came from. The Cl- would deprotonate it. So that's certainly occurring, but it's not productive, so we don't bother with it. How about rearrangement? Now, this particular guy can't rearrange to become any more stable, but even then, carbocations, which are on that carbon, we call these vinylic carbocations. Vinylic means it's on the carbon of the carbon-carbon double bond. These guys, as it turns out, for reasons of the way the orbitals are lined up, they don't rearrange very often. So even if they could, this guy can't become really any more stable. But if they could, they generally don't do it. All right, so let's see. Vinylic carbocation, rearrange. What's left over? Capture a nucleophile. What nucleophile should I capture? Water? Why not water? Water's an okay nucleophile for carbocations because they're desperate and not fussy. It's not there, right? This is to use the desperate, not fussy metaphor that some students would like to extend. This is like at 2 o'clock at the closing of the molecular singles bar, and that carbocation is so desperate that there's nobody there except the carbocation. So be as desperate as you want, but if there's no one there to bond with, you ain't going to bond. So the water's not present. I can't use it. I can use Cl minus. So there's our Cl minus getting captured. Draw in some hydrogens. And there is the HCl that we added. Does this addition that we've just written, does it follow Markovnikov's rule? Does the HCl add to the triple bond so that the hydrogen of the HCl becomes attached to the carbon of the triple bond that had the most hydrogens to begin with? Well, this is the end of the alkene that had the most hydrogens to begin with, 1 versus 0. So is that where the hydrogen of the HCl ends up? Yes, it is. So yes, follows Markovnikov's rule. Now at this point, you might say, okay, that's pretty good. It follows Markovnikov's rule. It does the same thing as an alkene does. But you might say, wait a minute. There's still a pi bond present. This is still an alkene. What do alkenes like to do when there's electrophiles around? Hint. What do alkenes like to do with electrophiles? In other words, are we done yet? Now, the reason we have to ask this question is, when we do a reaction, generally, everything is present all at the same time. Not necessarily in high concentration, but it's there at all the same time. So in every step in the mechanism, we can consider that we have reactants. We consider that all the intermediates in the reaction are present, as well as the products. So in other words, even though we've drawn a product, a perfectly happy-looking product, we still have to ask, can it continue to react? If it can, it probably will. So the question is, we look at this molecule and say, what functional groups are present? What do we have to react with? Well, we have HCl. What functional groups do we have? Benzene rings. Do benzene rings react with HCl that we know of? The sacred so far. This is the sacred temple of aromaticity. We do not enter there. Next week, we will go in and ransack that temple, but not this week. What do we know about carbon-chlorine bonds? So the only thing we've seen those do is be leaving groups for things like SN1 and SN2 and stuff like that. Have we seen that at an sp2 carbon? No, it was all sp3 carbon. So for the moment, we don't know anything to do with that. But we do know what to do with carbon-carbon pi bonds and HCl, because HCl still has a delta plus delta minus arrangement, so we can still protonate it once more. So I could put the hydrogen there, because it's an unsymmetrical pi bond, so I need to consider both possibilities, or I can put it on the end and make a different carbocation. What do I do? Can I get you to rewind the tape and play it for them? What's this thing called? Or what's this thing called? Carbocation. And I know you're good at this because you get the question right every time.
Okay. Resonance.
Right. Every time you see a carbocation in a reaction mechanism, regardless where it comes from, resonance. They both have resonance because of the benzene ring, but don't be fooled by that. It's the resonance that stabilizes the carbocation we're interested in. So this guy is primary. Does it have any resonance to stabilize that carbocation? No. This guy is secondary. The chlorine doesn't count towards that. 1, 2 carbon. Secondary. Does it have resonance? Yes, benzene ring. So how would we put the proton on? Would we put the proton on to make the first carbocation or the second one? Second one. Are you sure? Carbocations are unhappy because they're electron deficient on that carbon, open octet and positive charge. What does the chlorine do to that? How electronegative is chlorine? If your neighbor is chlorine and you're already poor, right, you can't pay the rent. Along comes your neighbor, chlorine. Does chlorine help? Isn't chlorine pretty electronegative? Isn't it sucking electron density away? Right? Isn't this chlorine with its 3 lone pairs sucking electron density away and making that positive charge bigger? Sucking electron density away through the sigma bonds or through space is called the inductive effect. Can the chlorine do anything other than inductive effect? Can this chlorine atom right here, with its 3 lone pairs next to the positive charge and the open octet on carbon, do anything besides inductive effect? Yes. What can it do? Attack it? Donate it. There's a specific word we use. Thank you. Resonance. Open octet plus lone pair become, let me erase this here, become pi bond. How good is this new resonance contributor? Does it help or hurt compared to what we started with? Remember, just because we can draw a resonance contributor doesn't necessarily mean it helps the circumstance. We have to ask how good, how significant the contributor is. If it's a minor contributor, then it may not add very much. Is this new contributor I've drawn, the one with the double bond and the positive charge on chlorine, more or less significant than what I started with? Single most important rule for evaluating the relative significance of resonance contributors. If you remember back to 14C, we call this the ring of power rule. Remember the ring of power? You might remember the ring of power? Right? Short people fighting, elves fighting, dwarves fighting, orcs fighting. Everybody fights over jewelry. That's why my wife loves that movie, because they're fighting over jewelry. Right? Full octet. Yeah, this structure has every atom with a full octet. Sure, it has a positive charge on the more electronegative atom. That's less important than having an open octet. So that chlorine is electron withdrawing through an inductive effect, but electron donating through resonance. And which one of those two effects do you think wins out, resonance or inductive effect? Resonance usually beats inductive effects. In other words, this contributor was really important. Everybody is a full octet. So don't just think of it as secondary with resonance because of the benzene ring. The chlorine matters as well. So this is definitely the carbocation we want to move forward with. So while I'm erasing and you're drawing a carbocation, in your mind you're thinking, as you're drawing, thank you, as you're thinking about this carbocation, we've already evaluated resonance and decided it has wonderful resonance with the chlorine. So after resonance, you think about 3 fates. All right, some people got it. What should we react it with? Should we lose a proton? Sure, it goes right back to where we came from. That's happening, not productive. Can we rearrange? Well, you can rearrange, but it's certainly not going to be an improvement. So what's left? What nucleophile should I capture? How about Cl minus again? Put another one of those on there. And now I'm out of things to do, out of pi bonds. Markovnikov's rule followed. Is that second HCl molecule that's added? Is Markovnikov's rule followed there? Did the H of the second molecule of HCl add to the carbon-carbon pi bond so that the hydrogen of the HCl became added to the carbon that already had the most hydrogens to begin with? That's why we say Markovnikov's rule, them that has gets, because it's much easier to say it that way. Did them that has get? Yes. So follows Markovnikov's rule. So alkene and alkyne add the same way, follow Markovnikov's rule, whether it's HBr, HCl, HI, all add that way. And that's controlled by carbocation stability. Now, let us look at a different electrophile. Let's add water. Remember, in the beginning of all this, I said we could take this guy, react it with a molecule of water, and make ethanol. And maybe you can see the pattern. There's the molecule of water. We have 2 new sigma bonds that we've replaced the carbon-carbon pi bonds. We have an issue, or are we okay? We're cool? All right. So we've added the molecule of water in the same way we've added the HBr, the HBl, at least, or HCl, at least in terms of how we draw on the product. Let's work out a mechanism, see if it works the same way. So how would this go? Here is our alkene. There's our water. We said the alkene would be the nucleophile, so the water is the electrophile. And yeah, it looks like it's an electrophile. Delta plus on the hydrogen, delta minus on the oxygen. Hydrogen is less electronegative than oxygen. So it looks like it's going to start the same way. Proton there, positive charge carbocation there, plus what's left of the water, which is a hydroxide. And what do you think about this? Turns out if you take an alkene and dump it in water, they just kind of sit there and look at each other. It's like a 6th grade dance. How many of you remember 6th grade dances? Nobody? You kind of wiped them out of your mind? All right, 12th grade dances. In 6th grade dances, Billy's on one side of the gym. Well, Billy's on one side, little Janie is on the other side, and the lights are very bright because it's 6th grade. And the music is playing, and there's nobody in the middle, right? Because they don't particularly have a great affinity to dance at that age, right? Well, that's what's going on here. These two really don't have a great interest in each other, not because that OH bond isn't polar, but in fact because, well, this is a proton transfer reaction, right? How strong of an acid is water? Water. No, don't need any painkillers. How strong of an acid is water? It's a pretty lousy acid, and this is not a great base. This is a lousy base. So this is kind of a lousy process to do, principally because this guy is a strong base. It doesn't really like breaking that OH bond in water to become hydroxide. All right, so if the issue here is that HO minus is a strong base, it doesn't like to break away from the hydrogen. I'm not quite using the term leaving group because conjugate base is a little bit better term. It's not breaking away from carbon. Nonetheless, if that's the issue, how can I make it better? What can I do to water to enhance its electrophilicity, to make the part that goes away easier to go away? We've done this before. Protonate it. Yeah, if I have a proton on here instead, now you've got a much weaker conjugate base, more inclined to leave. And on top of that, because now this oxygen is burdened with a full positive charge instead of neutral, it's much more electron deficient, so the delta plus is bigger. In other words, H3O plus is a stronger acid than water. Turns out H3O plus will react with alkenes, excuse me. So how do we do that? Well, let's, instead of using the ethylene, we're going to use isobutylene, the same guy we used before. H3O plus in some form, like, for example, aqueous H2SO4, frequently used in that way. Remember, when you see aqueous strong acid, that means really H3O plus. Aqueous H2SO4, aqueous HCl, etc. If it doesn't say aqueous, if water isn't written, then that would just be pure H2SO4. All right, H3O plus, how are we going to do this? What is our product going to be? Let's work out the mechanism. And again, when doing a mechanism for a reaction that you've never seen before, you start by saying, hey, what do I already know? What are the functional groups present? How do they behave? What do they do that I already know? Alkenes, we've only seen alkenes do one thing up to this point, and that's be a nucleophile. It's to provide their pi electrons to make a new bond. H3O plus is even more focused in its purpose in life. As you go through organic chemistry, you'll see all sorts of interesting things that alkenes can do, but H3O plus will only ever do one thing. Bree, how many years have you been studying organic chemistry? 7. What have you seen H3O plus do? One thing, only ever one thing. It protonates stuff. That's all it does. H3O plus gets up in the morning. It doesn't even shut the alarm clock off because it's not on its to-do list. It looks on its to-do list. It's the same thing today as it was yesterday and the day before, and it will be tomorrow. It says one thing: find something to protonate. That's all it does. Very simple. Doesn't have to take 14D exams, doesn't have to study, doesn't have to take a shower in the morning, doesn't have to go to Starbucks. That's kind of sad, but unless you like someplace better than Starbucks, that's all it does is protonate stuff. So when you see H3O plus in a mechanism, you know something's getting protonated. Well, there's only one thing to protonate, that's the pi bond. So there is our protonation. Oops. I'm going to put the proton on the CH2 end of the pi bond as opposed to the other end of the pi bond. Why should I put the proton here to make this guy as opposed to putting the proton here? Why should I do that? Hey, what's the mechanistic basis for Markovnikov's rule? Yeah, more stable carbocations. Exact same thing we've been arguing all along. It's simply the more stable carbocation. Maybe some of the primary carbocation is produced. I don't know. We're just going to talk about the major pathway. All right.
Resonance.
Right. Every time you see a carbocation in a reaction mechanism, regardless of where it comes from, resonance. Maybe you should write that on your hand. Well, don't write it on your hand. That's not a good idea. If you come into the exam with stuff written on your hand, we won't like that. Write it in your mental hand, right? Every time you see a carbocation in a reaction mechanism, regardless of where it comes from, resonance. Does this guy have any resonance? No, so it's not an issue here. So then what are we going to do next? Three fates. What are the possibilities? In random order, rearrange. It's tertiary. It can't get any better than tertiary in this particular circumstance. Okay. What about lose a proton? BD protonated form of pi bond. Is that a possibility here? Certainly is, but it's not productive. It goes right back to where it came from. That proton is going on, off, on, off. Although it spends more time off, more time is in alkene. You know, proton on, proton off. Karate Kid, wax on, wax off. No? Go look it up on Wikipedia. So rearrange, probably not going to happen. Lose a proton, not productive. That leaves us with capture a nucleophile. What nucleophile should I capture? Why not Br minus? We've used that one before. It's not present. You can only use what's present. Water, we generated water in this step. And even if you don't remember that, generally H3O plus comes with water anyway. So there is our water. Should we be complaining about the fact that water is a crappy nucleophile? No, because this carbocation doesn't care. It is desperate and not fussy. So water, plenty good for that purpose. All right, so that takes us up to an oxonium ion. And for the most part, oxonium ions are not the kinds of things we have as reaction products, partly because oxygen doesn't like to have a positive charge, although we're going to get rid of its positive charge by giving that positive charge to another oxygen. If water is the solvent here, if there's a whole lot of water present, remember this is aqueous H2SO4, lots of water, so that means there's a whole lot of water present, and what we're going to do is do this deprotonation. That's going to be an equilibrium process. We'll talk about that in a second. So why does this even happen? It's not an improvement in stability, really, because we're taking oxygen with a positive charge and 3 bonds and 1 lone pair and no special stabilization to another oxygen with 3 bonds and 1 lone pair and no special stabilization. So that's 50-50, but there's a whole heck of a lot of water. It's the solvent. What did Le Chatelier say when you have a whole lot of something? You use it up. The equilibrium tries to shift to get rid of it. So by having a whole lot of water, we're putting pressure on this side of the equilibrium. It shifts in that direction, and we end up with a proton more attached to water as H3O plus than attached to the alcohol. All right, so let's ask ourselves, does this reaction follow Markovnikov's rule? Does the HX, in this case X is the OH group, get added to the alkene in a way that the H becomes attached to the carbon of the alkene that had the greatest number of hydrogens to begin with. All right, there's the, maybe if I draw it that way, it'll be a little easier to see. There's the molecule of water that we added. Does the H of the water become attached to the carbon that had the most hydrogens to begin with? Yeah, this follows Markovnikov's rule. Another thing that follows Markovnikov's rule. Now, something else you might notice about this. Does this combination of alcohol plus H3O plus look familiar? Remember back when we talked about E1 reactions? Right, we said if we took an alcohol, and you could remove a molecule of water from an alcohol by taking the alcohol, adding H3O plus, that protonated the alcohol to make it into a leaving group, not a great leaving group, but still a leaving group. If that leaving group leaves, then we get a carbocation, and one potential fate of a carbocation is deprotonation. In other words, the forward direction is electrophilic addition to a pi bond. The reverse direction is E1. So these two processes are in equilibrium with each other. Now that brings up a question. Here we have alkene plus H2O in equilibrium with alcohol. Now I haven't written the acid because the acid is not part of the balanced equation. We have an equilibrium. How do we control this then? In this direction it was E1, in this direction it was addition. How do we control that? Turns out in the laboratory we can play games with this by taking advantage of Le Chatelier's principle. If we want alcohol, we simply use a lot of alkene and or a lot of water. And since most of the time water is much less precious than the alkene, then we simply use a lot of water and drag the equilibrium in that direction. Or if we have an alcohol and we want to make alkene, then we either remove water and or alkene as it's formed. And so you can manipulate, on paper at least, manipulate that equilibrium. We assume on paper we have control over it. Now something else I'd like to point out about this process. We started the reaction by adding H3O plus to the alkene in the first step. And in the last step, our H3O plus came back. What does it tell us about the nature of H3O plus in this reaction? It is, no, it's not quite enzymatic, but enzymes do this. You're thinking along the right line. It's a catalyst, that's right. Anything that you put, anything that's in the beginning that's regenerated later on in the mechanism is a catalyst. So this H3O plus can cycle around, protonate another one, we go through the whole mechanism, generates a new H3O plus, and so on and so forth. So you really only need a small amount of H3O plus to make this process go forward or backwards. Now what I want to do here is talk about doing this with an alkyne, just like we did with HBr and HCl. So let's see where that goes. Let's talk about an alkyne hydration. So when you talk to your parents or your friends today, and they say, "What did you do in Chem 14D?" Because they're living vicariously through you. They can't be here, so they want to be here. And you say, "Oh, we learned all kinds of stuff today." Add drum beat here. All right, alkyne hydration. Let's take, we did phenylacetylene before. Let's do phenylacetylene again. H3O plus, aqueous HCl. What should happen? We've seen that these addition reactions, where you have HX, in this case the X is the water of the H3O plus. When HX adds to the pi bond, we replace the pi bond with two new sigma bonds, one to hydrogen, one to X, and the hydrogen goes to the end of the pi bond that had the greatest number of hydrogens to begin with, Markovnikov's rule. So that much of the molecule remains. The hydrogen of H3O plus goes here. The OH of the water that we've added goes there. Anybody care to dispute that? Looks good to me. It's the same pattern. Now, I do want to point out before we talk about this mechanism that what you should begin to see, this is probably the first time you're probably really beginning to see these kinds of patterns in terms of the way functional groups react. If you look for those patterns, it will make your life significantly easier as this course goes on, especially when we get to carbonyl chemistry in week 7.5, 8, 9. By then, if that's kind of a little late to get into the patterns, but it'll definitely be useful. I'll try to get into pattern thought early on. All right, so confident in our prediction that this reaction should make, we call this an enol, by the way. En for alkene, ol for alcohol. I debated as to whether or not I was going to leave that fact in, but I thought I would keep it in. Yeah, I just wanted to be enol retentive. If you don't understand, talk to your friend who's a psych major. All right. Anyways, that's an enol. So confident that this is what's going to happen, feeling good in all this mechanisms we learned in 14D so far. So we go to the laboratory, get phenylacetylene, add some aqueous HCl or aqueous sulfuric acid, stew it up, get the reaction product out, and say, wait a minute, we have to check and make sure it's what we think it is. So we go back and do spectroscopy. Remember spectroscopy? So you say, let's see, IR, I should see a benzene ring, an OH, and a carbon-carbon double bond. Well, you're 1 for 3. The product you actually get out of this reaction does have a benzene ring, but it has no carbon-carbon bond. It has no OH. In fact, it has a carbonyl. Huh? Well, let's figure out. Mechanism. What's going on? Mechanism is the answer to every question. Well, almost every question. Yeah, resonance is the answer. And sometimes the answer is just no, but... All right, so mechanism. What's going on here? Phenylacetylene, hydronium ion. How should we start? What does hydronium ion do? Protonate stuff. That's what it does for a living. That's what it gets paid for. When you look at the resin, if you're on, like monster.com and you're looking, this is not a paid advertisement. If you're looking at monster.com and you find the resume of H3O+, it's very simple. Education, none. Salary, don't need any. Job skills, protonate. That's it. Very simple resume. What's it going to protonate? Benzene ring? No, that's still sacred. Carbon-carbon triple bond? Pi bond's good for protonating. Let's do the protonation. That gives us a carbocation. We're going to, again, 2 carbocations to consider, but that's clearly the more stable one. We just made that exact argument over there earlier when we talked about HCl. So what is this carbocation going to do? Every time you see carbocation interaction mechanism, you think about resonance. Yes, it has resonance. 3 fates. In this case, the resonance isn't going to lead to new products because there are other resonance contributors that would put the positive charge out here on the benzene ring, and if in fact you accepted a nucleophile there, you would pay the price of aromaticity. Not good. So what do we do instead? No resonance. Next thing we think about is 3 fates. Rearrangement? No thanks. That's a good way to put it. Can't really make it much better. How about lose a proton? Sure, it can go right back where it came from. So we're left with capture a nucleophile. You kind of see the patterns here. Carbocation captures a nucleophile, leads to addition. Not all the time. When we start our next lecture unit, we're going to talk about carbocations capturing nucleophiles and leading to substitution, or being deprotonated, leading to substitution. But for the moment, capture a nucleophile. What nucleophile should I capture? Water. Capture water. Oops, I'm just going to put it over here. It'll be easier. We have another oxonium ion. Oxonium ions, as it turns out, have fates just like carbocations. There's a very limited number of things they can do. But one thing we've frequently seen oxonium ions do up to this point is be deprotonated. Like here is an oxonium ion being deprotonated. How about that? What should I deprotonate this particular oxonium ion with? Water. Why not hydroxide? That's a much stronger base. Why should I use water? Water's a lousy base. I'm sorry? Well, it's more than there's, well, more of it, that's one way to put it, but to be a little more blunt, the reason I can't use hydroxide is because it's not even present. And you kidding? This is acid. What happens when you take strong acid and mix it up with hydroxide, which is a blank base? Strong base. What happens when you take strong acid and strong base? Neutrality. So you don't have strong acids and strong bases together in the same reaction. All right, so there's our deprotonation, just like we did before. That's that Le Chatelier's principle-driven kind of thing. And here's our product. Gosh darn it, it's that enol. The one that we didn't get. The one that if we went to the laboratory and ran the reaction, this is not what was formed, but it's formed. Anybody have a problem with this mechanism? I don't. I like what's drawn up to here. It's perfectly parallel with all the other HX addition to pi bonds that we've seen so far. But this is where it becomes, this is where I have to do my Billy Mays imitation, which I'm not very good at. How many of you knew who Billy Mays was? Right? What did Billy Mays used to say? But wait, there's more. Because this is an alkene, and present with the alkene is hydronium ion. What do alkenes like to do with hydronium ion? What does hydronium ion like to do to alkenes? Protonate it. It's the same thing we've done how many times before? So protonate it. Now we get into a little bit of virgin territory here, so let's see what's going to happen. Because we haven't done the protonating of an alkene when there's we haven't protonated an enol, the alkene ol. So let's see here. Phenyl CCH2OH. That portion of the molecule stays intact. Now the question becomes, do I use the pi bond to make a new carbon-hydrogen bond out here and put the positive charge next to the oxygen, like so? Or do I put or do I make that second carbocation? First carbocation or second carbocation? I'll put some more chalk marks up here. Maybe it'll be easier to see. First carbocation or second carbocation? Right? It's like when you go to the eye doctor. Better or worse? Better or worse? Better? Why better? Resonance, thank you. Even if you just woke up, the answer is resonance. Lone pairs next to open octet. This is secondary with actually two things of resonance, the OH and the benzene ring. This is primary without any resonance, or no resonance that stabilizes the carbocation, so let's not even bother with that guy. Let's see, draw resonance contributors. There is an oxonium ion. Now, it's a new kind of oxonium ion because this one has a pi bond, but it's still an oxonium ion. It's an oxygen with 3 single bonds in a lone pair. What do we know that oxonium ions like to do? By the way, before we answer that question, this is another primary reason why when we have a carbocation, we think about resonance, because sometimes thinking about resonance contributors will lead you to the next step in the mechanism. So what do you think? It's an oxonium ion? What do we know that oxonium ions like to do? We know two things up to this point that oxonium ions like to do. They like to ionize to make carbocations. That's not going to happen here because you have to break 2 bonds. So what else do they like to do? Yeah, be deprotonated. What should I deprotonate it with? Of water. The strongest base that is present. It's not the issue that it's most prevalent, it's the issue that is the strongest. Plus H3O+. All right, so now that product, that ketone, that actually fits beautifully with the IR data. So this is the actual product. Now, it's also catalyzed because we get our H3O+ back. But we've seen that before. Other H3O+ additions to pi bonds are catalyzed. And this process is reversible. So you can protonate the carbonyl, go to the oxonium ion, draw its resonance contributor. You might think about it being deprotonated to go back and so forth, all the way back where we came from. Now you might say, I don't understand. The enol that we had here, right? So we deprotonated this, made this enol. This enol looked perfectly happy. It's conjugated. This guy's conjugated too. So why do we go up to this point? What's going on here? In other words, what we have is an equilibrium between this guy, which is the enol, and its isomer, which is called the keto form. This happens to be a keto, but it's not called keto because it has a ketone, but rather simply because it has a carbonyl in it. These kinds of isomers, they have the same formula, but they differ by the position of an oxygen and a pi bond. You will see these kinds of isomers occasionally, especially among carbonyl chemistry, but we're introducing them here. These kinds of isomers are called tautomers. And they differ conceptually by the position of a hydrogen and a pi bond. They don't differ that way mechanistically because I can't march the hydrogen over and just do it in one step. That turns out to be forbidden. You have to use the water, the H3O plus, to kind of shuttle it around. Now, why should one of these be favored over the other? They're both conjugated and so forth. The answer is this equilibrium lies on the keto side by 10 to the a whole lot, probably about 10 to the 6th in this particular case. And that's simply because if you add up all the bond energies of the enol side and add up all the bond energies of the keto side wins out by a couple of kilocalories. So for simple keto-enol tautomerizations, tautomer equilibria, the keto is more stable. When we talk later on in this course about enols, we'll see exceptions to that. But for the most part, the keto form is stabilized. Now, since we have a couple of seconds, and I know a question comes up at this point. Some people are going to say, we have a carbocation here. Instead of drawing resonance, why don't I just have that carbocation capture a molecule of water? In other words, take this carbocation, have it capture water. Actually, there's going to be two steps here, water and then a PT, a proton transfer. That would take us up to this point. What's wrong with that molecule? There's nothing wrong with this molecule. It's a perfectly happy molecule, but it's under these acidic conditions, so we can go back and sample other things. Whoop, positive charge. It can go back and sample other things. And I'll leave you as an exercise to think about how this, under acidic conditions, might be interconverted with the keto and the enol forms. And as it turns out, while this is a perfectly happy molecule, it's just not as stable. The keto form wins out. The ketone form, the carbonyl form, wins out for exactly the same reason. All right, what we're going to talk about next time is we're going to continue our exploration of addition to carbon-carbon pi bonds by talking about some other reactions, for which we will need our lecture supplement. That's what we're going to pick up next time.